Today let's continue building the clock. I've built the board here. You can see all the counters. This is count by 5. Actually it resets at Q5 and it counts from 0 to 4 and increments this chip. This chip divides it by 10 and we have 1 Hertz pulse here. Then the seconds counter, 2 chips, and 2 chips are needed. This chip drives the 1 segment, this chip drives the second 10th segment. So 1 second is handled by this chip, from 0 to 9 second is handled by this chip, from 0 to 5 is handled by this chip. Then there can be minutes. Of course it's the same, the hours have the same concept, and it's actually pretty same from the breadboard. I have connected a small capacitor. Well, small capacitor works because the clock is not drawing a very high current. These are not TTL chips, they are 4000 series logic chip which uses MOSFET and have very low idle current. It draws current only when it's switching. You can see the voltage regulator transistor, some base driving transistor for the regulator transistor. Then there is this basically transistor. So basically it is switching and it is producing a square wave which can be fed to the chip. So first I would like to measure some voltages on the board, and of course connect a fuse at the input on the board and also on the primary winding of the transformer. I didn't have 50 milliampere 220 volts fuse because I could not find them, so I've purchased this 40 volt 1 ampere fuse, and actually one of them is cracked. You can see it is cracked. Other 3 are fine. This one is a little cracked, but anyways, my point is to basically use a fuse at the input and also at the transformer output. So if anything goes short circuit, your house will not catch fire at least. So let's turn on the circuit, or actually the transformer which turns on the circuit. Now you can see the LED turns on, and this LED is in the voltage feedback, or basically it is acting as a current, it is acting as a voltage reference, and we can measure the diode drop of the LED. It is about 2.6 volts, 2.66 volts. The voltage on the chip is about 6.4 volts. It is nice voltage, and the rectified voltage is about 19 volts. It is also good voltage. So now I've measured the voltage on the circuit. I can actually also measure the AC voltage too, I guess. It's about 14 volts RMS. Scope, and first thing I will measure is the voltage on the base, or the waveform on the base. Of course make sure there is not very high voltage on the base of this transistor because it can handle only about 5 volts in reverse from collector to base or emitter to base. That's why TTL chips are limited to 5 or 7 volts maximum. And I will measure on the base of the transistor. It should be a square wave kind of, and it is actually a square wave with a peak to peak voltage of 1.2 volts, 1.4 volts, not 1.2 volts. This is the transistor switching and it is out of the basically scope range. You can see the voltage and the frequency. The voltage is almost, it is reading 7 volts, but it is not quite accurate, or it can be accurate, I don't know, but you can definitely see the waveform here. It is nicely switching. We can also, of course there is 2 peak to peak value. We can switch this to duty cycle and see the positive duty cycle of the circuit. That is 52% because of the base diode, base to emitter diode. Now I will look at the output of this chip, which is pin 3, which is Q0 pin, and this chip is dividing by 5, so I should load the time base and probe it here. Now you can see a 10 Hertz pulses, or 10 Hertz pulses. Now it can be further divided by 10 and we have 1 Hertz pulses. Now you can see 1 Hertz pulses. It is nice pulse. Now it can be further divided by 10 by this chip, and it will be turning on for 10, basically turning on for 1 second and off for basically 9 seconds. You can see it turns on, then off for 9 seconds, then on again. 1, 2, 3, 4, 5, 6, 7, 8, 9, and at 9 it turns on and on for 1 second, then off. Now it can be further divided by basically 6, and it will be turning on for basically 1 minute. So it will be turning on for 10, this chip will be turning on for 10 seconds and off for 50 seconds. So it is 1 hertz pulses. Now you can see it is on for 10 seconds, and then it will turn off, and it will turn on again after 50 seconds, and it can be further divided by 10, and you will have a signal that is on for 1 minute and off for 9 minutes. Then it can be given to this chip, and this chip will divide that signal by 6 again, and then this chip will be turned on for basically 1 minute and off for 50 basically minutes, and it will turn on at every 1 hour. So that can be given to the hours counter. It will count from 0 to 9 and increment this chip. Now let's talk about the reset circuits of the chips. Well, the reset circuit is quite simple. I will explain you. Well, this chip is just dividing by 5. So you can see this is the reset pin. This is the reset pin and this is the Q5 pin. And at Q5 we want the chip to reset because we are counting from 0 to 4, which is 0, 1, 2, 3, 4, which is almost 5 steps. So after 5 steps you want to reset the circuit or the chip, and at Q5 we are resetting it. So we are having 10 hertz pulses coming out from the chip. Then it is given to this chip, which is just counting from 0 to 9. So there is no reset circuit connected. There is, you can see, the count inhibit and the master reset connected to ground or 0 rail. Then it counts and 1 hertz pulse go to this chip. This chip again is not resetting at any point, so there is almost basically no reset needed. So we have connected the reset pin and count inhibit pin directly to ground rail or 0, but this chip is resetting at Q6 because we want to count for 6 steps and reset at 7. So we can count again 0, 1, 2, 3, 4, 5, and at 6 we want to reset the circuit because it is active reset. As soon as the reset line goes high, the chip reset itself. So this chip, you can see there is this pin reset, master reset pin connected to Q6, and then we are incrementing this chip. This chip is again counting from 0 to 9 and incrementing this chip. This chip is basically resetting at Q6 again, same as this chip, but this chip again is counting from 0 to 9 and incrementing this chip. But there is a catch. Well, when this chip reaches count 2 and this one reaches count 4, we want the reset circuit to reset both of the chips. Well, of course this can be done by connecting some AND gate circuit, and you can use transistor AND gate, TTL AND gate, or any AND gate, CMOS AND gate, but I'm using just 2 diodes. You can see there is a diode connected from here to Q basically 2, and this diode is connected to basically Q4. So when both of the outputs are high, these diode will not conduct, and the circuit or basically the resistor will pull the master reset pin high, and it will reset both of the chip. And when this chip is 0, it will basically draw some current from the resistor to back to the input pin or basically the chip to the ground. So that's how the reset is working. Well, let's talk about how the chips are incrementing, because let's say this chip is counting from 9, and then we want to increment to basically from 9 to 0, but there should be 1 in this chip. So when should we increment? Well, these are rising edge chips, and as soon as there is a rising edge, these chip will basically increment. So if we connect Q9 to this chip, and as soon as Q9 goes high, this chip will increment. Well, there is no problem in connecting the basically chip to Q9, but of course when the Q9 goes high, the display will be showing 9 and again 1 at the display. So there is 1 and 9, which will look wrong or very wrong. So we want to increment this chip when this chip counts from 0 to 9 and resets back to 0. So basically when this chip is at 9, this chip is at, let's say, count 0 for now, and when this chip goes from 9 to Q0, this chip will increment and it will look correct. Basically this chip goes to 9 to basically 0, so the display will be showing 0 number, and then this chip will increment and there will be 1 and a 0. So that will tell us that there's about 10 seconds on the chips or on the display, and it looks correct. Now there is a catch. Well, these two chips when are 0, we want to increment the minutes counter. So we can again use some kind of this circuit or exactly this circuit. So basically in this chip, and Q0 and Q0 will go to this diode, and there will be a pull-up resistor. But of course there is again a catch. When this chip is at 9, let's say this chip is at basically Q5, so this chip is at 9, it will go to basically 0, it will increment this chip will try to go to Q6, and at Q6 it will reset and it will go to 0. So there is 0 0 already decoded in the circuit, so we might not need AND gate but only connect Q0 to the clock input of this chip. So if this chip counts from 0 to 9 and again 0, this chip will increment. But of course there is again a catch. When you turn on the circuit, all of the bits will go up, Q0 bits will go up. So what can happen is that the chips might self increment on the startup, but that is not a problem because even BCD chips turn on at random values, or basically random values on the chips, or random pins fire, then it is counting. So there is a way we can connect basically all of the reset through some logic, and on the startup we press the reset and set the time. But of course I'm not doing that. Basically there will be a switch to basically set the time on this chip and this chip. I don't care about the second chip. So basically if I'm setting the time right and there is no light out, or if the transformer is not burning, the chip will count and my clock will still work. So that is not a problem for me. And even if I use a falling edge counters and connect it to Q9, basically on the startup the Q9 is low, so the chip will increment anyways. So there is basically nothing you can run away with. So that's how the incrementing and resetting circuit is working in this chip, and it is a ring counter chip, not a BCD chip or binary counter chip, resetting at basically 9 or at 10. So thanks for watching the video. I hope you liked it, and the next video I will try to connect some display driver, and I will connect this logic board to that display driver. And make the time setting circuit simple, I will use this kind of toy switch, and basically there can be two clocks, basically clock coming from the minutes counter to the hours counter, and clock coming from the seconds counter to minutes counter, and they are not very high frequency, it is super low frequency. So I can use the chip. Well, the right pin can go to the seconds counter, the left pin can go to some push button and some basically some non-oscillating circuit like Schmidt trigger, or basically some simple RC network. So when I press this switch, this switch doesn't bound and increments the minutes counter fast. So when we press the button, the chip will increment and we will set the time. So basically the middle pin will go to the clock input of the chip, the right pin can go to basically the seconds counter, and the left pin can go to some push button, and same with the circuit. I will use another identical toy switch and connect the left pin, or actually the right pin, to this minutes counter, and left pin to basically some push button, and middle to the clock input. Well, it doesn't matter if you connect left or right pin to any basically clock source. You can also use a counter 1 Hz per second or 2 Hz per second. Or what you can do is that you can take from 1 Hz from the circuit and basically connect it to the left pin, and right pin goes to the second counter. So basically when you switch to the right position, the 1 Hz pulse will be connected and it will start to increment, but it will be slow, time consuming. So a push button may work here. So I will connect the switch in my next video. Thanks for watching the video. I hope you liked it.